Swayam Prabha. Digital India. Educated India.
So continuing from the previous lecture, the mass transfer rate can be written in two ways. Okay, one is using the fundamental laws of diffusion. So we can write the mass transfer flux based on the F-type mass transfer coefficient. Okay, so this is one possibility. So in this case, this mass transfer coefficient F is related to the diffusion coefficient DAB in this way. Okay, where Z here is Z2 minus Z1. So this is one way of writing the mass transfer flux, which we call this is fundamental laws of diffusion based analysis. The second one is phenomenological. Where we write flux is equal to some coefficient times the driving force. So these are two ways of writing the mass transfer flux. This particular phenomenological approach is similar to how we write heat transfer flux, where we write Q is some heat transfer coefficient times delta T. Okay, so it has analogy to this. So if you suppose if you take this is equation 1 and this is equation 2, by comparing this equation 1 and 2, we can also relate the mass transfer coefficients used in these two approaches. Okay, so let's say equating this equation 1 with the 2, so we have Na is equal to F by CBM. Here the CBM is the log mean concentration difference of the species B, which is non-diffusing in this case. So by comparing these expressions, we see this coefficient F, the local mass transfer coefficient F, is related to Kc times CBM. When we use these expressions for gases, for gas phase systems, we can relate concentration in terms of pressure as C equal to P by RT, and then we can write this CBM in terms of pressure also. PBM by RT. So F can be related to Kc PBM by RT. This is for gas phase. Now you can also see the units of coefficients F and Kc from this set of equations. You will see this from equation 1, which is written as Fa equal to Na equal to F times Ca1 minus Ca2. You can see this CBM is also in concentration units. These are also in concentration units, so they cancel. So the units of F will be same as the units of Na, which means F will be in the units of moles per meter square second, okay, or moles per unit area unit time. You can use other units of meter, second and moles. Whereas from equation 2, where we have written Na using this phenomenological approach, so if you substitute the units, you will see for Na this is moles per meter square per second, Kc will keep it like this, and concentrations are given in, let's say, moles per meter cube. Then this makes the units of Kc in meter per second. I cannot emphasize more on the importance of the unit systems when we deal with the mass transfer coefficients. Whenever we change the units of the driving force, correspondingly the mass transfer coefficients units will also change. So it's very imperative, very important to make sure you are using the right units for the mass transfer coefficients, whether it is K type or F type. So all this discussion so far is pertaining to diffusion of A in non-diffusing B. We can do the same thing for equimolar counter diffusion also. So if I consider equimolar counter diffusion, in this case NB is equal to minus Na, so Na plus NB equals to 0. So therefore in our fundamental laws of diffusion, this expression simply becomes just Ja, because this term goes to 0 for equimolar counter diffusion. So we have Na is equal to minus dAb dou C by dou Ca by dou Z. So at steady state, we can integrate this equation and we will get Na is equal to dAb by Z Ca1 minus Ca2. Now if we want to write this expression in terms of F type mass transfer coefficient, we know that F is defined as dAb C by Z. So if you substitute this F in Na, you will get F by C into Ca1 minus Ca2. So this is from the fundamental laws of mass transfer for equimolar counter diffusion. In the case of phenomenological approach, we write Na is equal to Kc prime Ca1 minus Ca2. Here I am using this prime to denote this equimolar counter diffusion. Okay. Again, we are talking about differences in the K-type mass transfer coefficient under different diffusion conditions. When you are looking at diffusion of A through non-diffusing B, we simply use Kc. In the case of equimolar counter diffusion, we write Kc with a prime. Okay. So, Kc and Kc primes are different things. So, this is for equimolar counter diffusion. And this is for diffusion of A in non-diffusing B. So, between these two equations, we can relate and then see the relationship between F and Kc prime. So, we can see this F is equal to Kc prime times concentration C. Okay. Or if you want to write this in terms of pressure, it would be P total pressure by RT. Okay. So, this is the relationship between F and K prime C. So, in this case also the units of F will be in moles per meter square second, and this Kc prime will be in the units of meter per second. And you can see the relationship between F and K is different in the case of equimolar counter diffusion and in the case of A diffusing through non-diffusing B. So, it is important to know these relationship, which also depends on the nature of diffusion. So, the reason of discussing this is twofold. One is we are able to establish the relationship between different kinds of mass transfer coefficients F versus T, F type and K type. Secondly, when we deal with the mass transfer operations, absorption, distillation, drying, humidification, whatever, so we are always going to use the phenomenological approach. Okay. However, the point of this particular discussion is that even though we write in terms of phenomenological equations, you can always relate that back to laws of diffusion. Okay. It is for a mere convenience and analogical treatment of heat transfer and mass transfer that we write phenomenological equations for mass transfer rate in mass transfer operations. Okay. However, when you deal with more general cases, we can always go back to the fundamental laws of diffusion approach and get the exact expression also. Okay. So, phenomenological approach is only for the convenience and for making analogy to the heat transfer. So, subsequently, now we can write, so let us write this here, in mass transfer operations, phenomenological rate equation is used. Okay. Also, when we look at the variety of mass transfer operations, the driving forces are also expressed in different kind of quantities, mole fractions, partial pressures, mole ratios, etc. So, we would like to list out all possible phenomenological rate laws and the corresponding coefficients and also relationships. Again, we are going to do this for both equimolar counter diffusion as well as diffusion of A through non-diffusing B. So, let us take the first case. Diffusion of A in non-diffusing B, which is basically characterized by the fact that NB is 0 and NA by NA plus NB is 1. So, here we will write for gases sometimes we write fluxes in terms of partial pressures of species A, and correspondingly we introduce a mass transfer coefficient Kg. We could also write this in terms of mole fractions. Here Ya is the mole fraction of species A in a gas phase, and the corresponding mass transfer coefficient Ky. Or like I discussed before, it can be written in terms of concentration units also. And for liquids, we write Na is equal to Kx Xa1 minus Xa2. Here X is reserved for liquid phase composition or liquid phase mass transfer. X here is the concentration mole fraction of species A in a liquid mixture, and this is the corresponding mass transfer coefficient small kx. You can see I am using unique set of mass transfer coefficients depending upon the driving force expressed in different units. You can also use this Kl when we use molar concentration in the liquid phase. Okay. So there is a difference between these two expressions. Here when we write Ca in the gas phase, we can relate this to pressure. Concentration is written as P by T, P by RT. Whereas here in the liquid phase, concentration means it's a molar quantities, how much moles per unit volume of the solution in that sort of units. Similarly, we can write similar set of equations for equimolar counter diffusion. In gases, so here this is described by the fact that Na is equal to minus Nb and Na plus Nb is 0. This is the characteristic of a equimolar counter diffusion. For gases, we write Na is equal to Kg but with a prime. You can compare these two equations. So they are essentially the same thing. I am only making a differentiation between the mass transfer coefficient Kg versus Kg prime because I want to distinguish between different kinds of mass transfer modes here. One is diffusion of A in non-diffusing B, other is countermolar equimolar counter diffusion. Similarly, we can write Ky prime and Kc prime. For liquids, Na is written as Kx prime Xa minus Xa1 minus Xa2 or Kl prime with Ca1 minus Ca2 as the driving force. So you have to keep kind of note of these different ways of writing the mass transfer rates. And the corresponding mass transfer coefficients. Okay, so that's the point I'm trying to make here. So now I already established one case where the F type and K type are related by writing the two approaches and then equating the fluxes. Now you can do the same thing for all the other driving forces that I just mentioned. So I'm going to just write the relationship, and it's something easy to verify, cross verify. Okay, so again for the first case, so this is basically relationship between F type and K type coefficients. So all these quantities ppm or xbm, these are all log mean difference, concentration difference of the component B. Okay, so these three are for gases and the last two are for liquids. Now writing for equimolar counter diffusion, an important thing to note here is only in the case of equimolar counter diffusion, the both coefficients F and K are equal only for concentrations expressed in terms of mole fraction in gas phase or in mole fraction in liquid phase. As long as you write them in terms of mole fractions, in the equimolar counter diffusion, the F type and K type are actually equal. For all the other cases, there is always a factor of there's a factor that has to be multiplied or divided. Okay, so do not simply interchange F type and K type. Okay, the reason is the mass transfer coefficients sometimes are reported in F type, but we may want them to use in K type in mass transfer operations. So these are the relationship to use to convert the coefficients between the two types. Now the next topic of interest is the mass transfer coefficients. They are obtained by either theoretical analysis or correlations, or these correlations are typically from experiments. Okay, so having defined all these different types of mass transfer coefficients, F type, K type, depending upon the driving force, now where do we get these mass transfer coefficients from? Okay, there are two sources. One is we can set up a simple theoretical analysis and then calculate the mass transfer coefficients, or we can conduct extensive set of experiments under controlled conditions and then express these mass transfer coefficients in terms of some non-dimensional numbers. Okay, those are called correlations. You must have studied heat transfer coefficient correlations, okay, or friction factor correlations. In the same way, there are correlations available for mass transfer type coefficients also. Okay, so again, what I'm going to discuss now is something that you might have already studied. This is more like a revision. In terms of a theoretical approach, you could have what is called this, if you have a simple a gas flowing through a falling film on a wetted wall column. So a falling film, so liquid falling film case, this coefficient KL is given as something like 3.41 DAB by delta. Okay, so this is a very simple. So you can see this L here means it is a liquid phase mass transfer. And what is the driving force used in this case? Mole fraction, concentration, mole ratio, partial pressure. It's concentration. If you go back here, the way we have defined, KL is defined here. Okay, that means the expression for KL I have written there is based on some mass transfer experiment or mass transfer theory in which the flux was calculated based on concentration as the molar concentration as the driving force. That's why we are using KL. So look for any correlations or any mass transfer expressions would have an associated driving force from which it is calculated from. So it is important to match that. So in this particular case, when I say DAB for a falling film experiment, when we say KL, it means that the driving force was molar concentration, mole per liter, mole per meter cube. This delta here is related to the thickness of the falling film. DAB is the diffusion coefficient. Sometimes what we do, we kind of combine these mass transfer coefficients in some sort of non-dimensional number. For example, if you define KL delta by DAB, this is known as Sherwood number. This is equivalent to Nusselt number in the case of heat transfer, where Nusselt number is defined as something like HD by K. So K here is thermal conductivity, D is some length scale, and H here is the local heat transfer coefficient. In the same way, here KL is the mass transfer coefficient, delta is a length scale representing the mass transfer. In this case, it is the thickness of the falling film, and DAB is the mass diffusivity. Here we talked about thermal conductivity, so here this is mass diffusivity. Okay, so we call this Sherwood number as something like SH. Okay, so this expression in terms of non-dimensional number can be simply written as Sherwood number is about 3.41. Generally, information is available in terms of this non-dimensional number. Once you know the Sherwood number, you can go back to the definition of Sherwood number and calculate the mass transfer coefficient. Then there are theoretical approaches like Higby's penetration theory, which sort of predicts KL as square root of DAB divided by pi theta, where theta is some time constant or time scale associated with this penetration theory. Or we have this Dunkwert's surface renewal theory, which predicts KL to be equal to DAB times some factor S, where S is called the rate of renewal of the fluid element or renewal rate. And these are very simple theories, but then if you want to go for a little more sophisticated theories, what you could do, you can actually combine momentum balance, mass balance together with a boundary condition, and you can solve for the concentration profile across the interface. Then you can use Fick's law, and from there you can get mass transfer coefficient also. This is basically what we call this as a boundary layer theory. Okay, boundary layer theory. So based on boundary layer theory, you might have studied heat transfer coefficient relations. In the same way, we also have expression for Sherwood number, which goes something like this. So here the skimming number is defined as mu by rho T. Okay, this is very similar to Prandtl number used in heat transfer. Okay, so an equivalent expression that you might have studied in heat transfer is Nusselt number written as 0.664, Reynolds number power 0.5, Prandtl number power 1/3. Okay, so this is valid for laminar flow. So when you have a plate and a fluid is flowing past this plate in a laminar condition, and you're looking at the rate at which mass is diffusing from the solid surface to the fluid about, that can be obtained as a correlation like this. Okay. So if you know the flow conditions, you know the Reynolds number, you know the properties of the fluids, you know what is the Schmidt number, you put that here, you will get a value for Sherwood number. Once you have the Sherwood number, you can go back to the definition of Sherwood number and calculate the heat transfer coefficient, sorry, mass transfer coefficient in this case. Now these are all correlations, but there are also many other type. For example, we use what is called this Chilton-Colburn analogy. This is something used for heat transfer, friction factor in fluid mechanics as well as in mass transfer. So here we write this JD factor, which is written as some Stanton number times Schmidt number power 2/3. Here the Stanton number for mass transfer is defined as Sherwood number divided by Reynolds number times Schmidt number. For a particular situation, something like let's say you have a turbulent flow in a circular pipe, turbulent flow inside a circular pipe. For this particular specific condition, you would have expression something like JD is given as 0.023 Reynolds number to the power minus 1.17. Okay, so if you look at Perry's handbook or any other the textbooks I have suggested, you will see mass transfer coefficient relations for different flow conditions, turbulent flow in a circular pipe or over a plate or over a sphere. Okay, there is a very large variety of conditions for which correlations are available. Sometimes the correlations are available as a function of Sherwood number, or sometimes they are expressed in terms of this Chilton-Colburn analogy by defining this factor JD. So this is one particular example. So if you have a turbulent flow inside a circular pipe, the JD factor is given as 0.023 Reynolds number power minus 0.17. So now from this equation, we should be able to get the heat mass transfer coefficient. The way to do that is you substitute the definition of JD, which I have shown here. So you would write Stanton number to the power Stanton number times Schmidt number power 2/3, that is equal to 0.023 Reynolds number power minus 0.17. Then introduce the definition of Stanton number, which is Sherwood number divided by Reynolds number and Schmidt number. You have this. So from here you can solve for Sherwood number. So you'll get 0.023 Reynolds number power 0.83 and Schmidt number power 1/3. Okay, so then this Sherwood number can be, once you know what's the Reynolds number of this situation and what is the Schmidt number, you can calculate Sherwood number. Once you know the Sherwood number, you can use KL, some length dimension divided by DAB would be equal to your Sherwood number. In the case of this problem, D would mean the diameter of the circular tube. If you have a relationship for a spherical particle, D would be diameter of that particle. Okay, so for every problem there is a length scale associated with it. Okay, that length scale what goes in the definition of Sherwood number. Okay, so Sherwood number requires just a length scale. It's nothing unique about it otherwise. Okay, so you have to define a length scale for the problem. So like I said, there are references, Perry's handbook, where you can look it up for a given situation. What is a correlation that that is available? Sometimes you may not have correlations available for mass transfer, but for an equivalent condition, you may get an expression for heat transfer. Okay, in that case, you can still use the correlation developed for heat transfer by simply changing the corresponding non-dimensional number. You can use it for mass transfer. Okay, so when you have something like this, let's say you have an expression for Nusselt number. I am giving an example here. So this is the relationship for heat transfer occurring from a cylindrical pipe where the flow is perpendicular to the long axis. Okay, this is a flow condition. So you got a hot circular tube, and the fluid is flowing past this tube perpendicular, and you're looking at what is the heat transfer rate or heat transfer coefficient for this particular problem is given by this. Okay, this information is available in the literature, reported. Now let's say you have a problem where you are looking at a mass transfer problem. Okay, maybe a solid is cylindrically available and a fluid is going past, and this solid is dissolving in this liquid. The mass is getting transferred from the solid block to the liquid, but we don't have a mass transfer coefficient for that situation. Let's say in such a case, we can use this particular heat transfer correlation and get the corresponding mass transfer coefficient. The way you do that is you replace the Nusselt number with Sherwood number, keeping all the coefficients same. Instead of Prandtl number, you are going to use Schmidt number, and this works just fine because of the fact that we have written the heat transfer rate, mass transfer rate analogically the same with the different driving force. Otherwise, the form of the equations are the same. Okay, so these are all the things that I want to say about mass transfer coefficient. These are very general discussions. Going forward, when we look at a particular mass transfer operation like distillation or absorption, we will be faced with a particular situation, flow situations. Okay, in those flow situations, you may also have a complex flow condition. Okay, specific to those problems are also correlations available. So as we go along for a particular mass transfer operation, I will also introduce more such correlations in calculating mass transfer coefficients. Okay, so far this is a very general discussion about what is already known to you. Okay, there are specific relations that we have to discuss when we go forward into mass transfer operations. Okay.